and welcome everyone to day 3, last session of the day for Love Data Week. You're all very welcome. And a special welcome to Darshana, who's kindly agreed to talk us through how far is too far, distance-based diagnostics applied to count data today. So much appreciate Darshana giving up her time to do this. So I'm going to hand straight over to you, Darshana, and thank you very much.
Thank you. Hi, everyone. My name is Darshana Jayakumari, and I'm in my second year PhD in Hamilton Institute in Maynooth University. And today I'm going to talk about my PhD work that I do along with my supervisor, Dr. Rafael de Andrade Moral. And in this talk, I'm going to take you through a new distance-based goodness of fit diagnostic applied to count data. So here we go. Okay, so in this environment, we are really blessed with the amount of number of plants and animals we have, and in the ecology, to study these plants and animals, we try to count them by number of the plants or animals available, based on our interest, and we want to actually associate these counts to the some specific environmental conditions. And so in this presentation, throughout, I'll be dealing with the count data only. Okay, let's move on to the next slide. So here we look at an example in which we assess the effect of an insecticide action of an organic extracts of Anonymous plant on the pest Cytophilus semes, which is infecting the maize in Brazil. And what we do is, in a laboratory situation, we take a control and an experimental group. And for the control group, we do we spray the plants with water, and the same amount we spray the insecticide, the organic insects of this particular plant, on the corn plants, and we want to see, and we put the number of equal number of pests in both the control group and the experimental group, and we want to count the number of progeny, like how many insects emerge, like new insects, not the ones already there, after 60 days. So this is the perfect example for count data. And the basic model for the count data is a Poisson model. And there's a lot of math in here, but the function, the probability function of the Poisson model is given here. So what I want you to focus is, Poisson model is a single parameter model. Also, it's an equidispersion model, which means that the mean of the distribution will be equivalent to the variance. There's no dispersion associated with it. Okay. But let's look at the data, is it actually mean equal to variance? We calculate the mean and the variance, and the mean equal to 23.45 and the variance equal to 28.151, which is actually not equal. Variance is really greater than mean. So we say that the data is over-dispersed, the variance is really high. And we want to confirm this with the ANOVA output as well. And we say that the residual deviance is very much higher than the residual degrees of freedom, which kind of says that the data is over-dispersed. And we move on to a graphical diagnostic technique, which is called half-normal plots, where we plot the residuals, what we consider here is Pearson residuals, against the half-normal scores. And I'm not going to go in detail about the half-normal plot, but please have a look into the references section where the paper actually explains about the half-normal plot. And here, if the residual points are the small crosses there, and there's a simulation envelope which actually is around the residual points. And if the residual points actually falls inside the envelope, it says that, okay, the model really explains the data very well. But here, we actually do it with the Poisson, and the model here considered is Poisson, but the residual points are outside the envelope. That kind of means that the model is not suitable for this particular data. So what do we do? So the sad reality is, at least for the Poisson model, almost 90% of the time, the data is over-dispersed. So we want to actually look at the models which can account for the over-dispersion. So the models that will account for the over-dispersion that are considered in this project is negative binomial model, which we are considering for two variations, like quadratic variance function and the linear variance function. which we'll see in a minute, and also quasi-Poisson and the Poisson normal. And for the negative binomial model with the quadratic variance function, in the general case, negative binomial model means the number of failures, like it accounts for the number of failures before a success. But in this case, what we're interested is the variance function. And we see that the variance function, like the mean is actually like the quadratic, the variance function is actually the quadratic function of mean. And 1 by 5 is the dispersion parameter. Okay, we move on to the negative binomial with the linear variance function. And here the variance is actually the linear function of mean, and 1 by 5 again is the dispersion model. And for quasi-Poisson here, we see that the variance is actually a linear function of mean, and the phi is the dispersion parameter. And we move on to the Poisson normal, and the Poisson normal is the one which accounts for the observational random effects. And the random effects are like, it will account for the random effects like added onto every other data point. And we can consider this random effects as a vector, and which arises from the standard normal distribution. So these are the models which account for the overdispersion that we're considering in this project. And we now have to look into the half normal plots of these models. So now we have actually looked at the Poisson model already, but we see that Poisson model is not really doing a good job. We see the quasi-Poisson and negative binomial model and the Poisson normal. For all of these models, the residual points actually falls inside the simulated envelope. But okay, then how do we actually select a model? There's not, like, all these models are actually, like, according to what we said, the residual points are actually getting inside the envelope, and there should be something which distinguishes between this model. So that was the question which actually gave rise to the thought of this project. There's something we could do to distinguish between this. We could come up with some kind of a measure. Yeah. Okay. So this is actually a plot for overdispersed data, consider like half normal plot. And we say that point A, B, and E are falling inside the envelope. But how do we actually distinguish between these points? Which factor, which measure can be used to actually distinguish between these? Maybe we can consider the envelope width. And for these, because envelope widths are very different for these points. So we can add a penalization factor of the envelope width onto the distance measure, or like whatever measure we want to come up with, and say this actually accounts for some factor as a distinguish between these models. And also C and D, which actually falls outside. So what do we do then? Okay, also there's the envelope width is there, but there should be some difference between CD and also ABE. So we should look for what we can do there. Okay, C and D falls outside the boundary. So what we could do is we add a penalization factor with respect to the boundary distance of these points from the boundary. So that's how we actually introduced a new framework, which is a distance-based framework. And we add penalization factors as a function based on the envelope width f of w, and the function based on the distance of the residual point from the boundary, which is actually g of b. So we right away jump onto the distance framework, and we give like di is equal to ri minus mi raised to n into g of bi with an indicator function divided by f of wi. And ri minus mi is like a base distance, and it's actually calculated for both the norms like L1 and L2. And ri is the residuals of the ordered statistics. And what we are considered here is the Pearson's residuals, and mi is the medians of the residuals. And bi is the distance of the residual point from the boundary, and it is actually included with an indicator function, which indicates that, okay, this is like switched there. Its indicator function is equal to 1 if the point falls outside the envelope. And if it is equal to 0, that means the point is like falls inside the envelope. There's no effect of the boundary distance there. And wi is the envelope width, right, for every residual point. Okay, so what is the choice of the functions for the envelope width? when we consider W, we just wanted to go with the basic ones. And the envelope width is considered as like the upper limit of the simulation envelope minus the lower limit of the simulation envelope. And there were three options considered as 1, W, and W squared. And the choice of functions for the boundary width is like G of B is just basic functions. And the rationale for selecting those is like the function will increase and it saturates after a specified period of time, except for the linear function that you will see in a bit. And the baseline is specified already. So these are the functions we considered for B. Ratio function, like alpha plus gamma 1 into x by 1 plus gamma 2 into x, and hyperbolic tangent function, alpha plus gamma into tan h delta into x, and logistic, and the linear function, and 1 for the function when there is no effect for the boundary distance. So there is a option for B equal to 1, like G of B equal to 1, as well as f of W is equal to 1, then there is like no effect of boundary, distance from the boundary, and also the envelope width. And the constants alpha, beta, gamma 1, gamma 2, eta, and delta are the constants already specified. So we give values to them, it's already there. So this is what I meant when I said like the functions actually increase for a specified period of time and then it saturates. And this happens except for the linear function. So the simulations we considered are like, so for the simulations we considered a single covariate model, and the covariate is simulated from a normal distribution, and there is like two parameters involved, beta 0 and beta 1. And beta 0 and beta 1 is already specified, we give values to them. And the response variable is simulated from one of the parent models. When I say parent models, it refers to the models from which the data is simulated from. So the parent models considered are Poisson model, which does not account for the overdispersion. And all the other models that are considered after Poisson has a parameter which accounts for the overdispersion, as we saw earlier, which is negative binomial quad. So when I say negative binomial quad, it means like negative binomial with a quadratic variance function. And that is considered for two conditions like less overdispersion and a higher overdispersion. And the same with negative binomial link, that is with a linear variance function for less overdispersion and a high overdispersion. And we also consider Poisson normal with low overdispersion and high overdispersion. And the values that we gave for the low overdispersion is like 0.5, and for the high overdispersion is like 5. And these models were fitted onto Poisson, negative binomial quad, negative binomial link, quasi-Poisson, and Poisson normal. So, and these simulations were considered for like the number of simulation considered was like 1,000, and the number of sample sizes considered is like 20, 50, and 100. So we are moving on to the results part. So in this plot, we're considering the parent model as Poisson. So we're simulating data from a model which does not have overdispersion. And here, I want to say is like, okay, what I want you to focus is like all these rows look same. That means the functions. So this is actually a box plot for the log transform distances versus the combination of the function of W and the norm function. So here 1L1, 1L2, and WL1, WL2, and W square L1, W square L2 against ratio 1 logistic and hyper functions for different sample sizes, which is 20, 50, and 100. And we see here the row is actually the same, like all the rows. That means in the distance framework, the G of B is not making an effect. The distance from the boundary is not really making an effect on this. And so since it is not making an effect, I'll just focus on one of the panel, which is just select the ratio and we look closer. So here, since it's actually data is simulated from a model which does not account for overdispersion, the models look same, like it's the distance values are not really changing much, like there's no variation between the distance values. Okay, so next, I move on to the negative binomial. The parent model is negative binomial with the quadratic variance with a less overdispersion. Here also, it's the same plot again, but here also the rows actually look the same. There's no difference between the functions as such. But when we look closer to one of the panes, we see that, okay, the Poisson actually has a higher value than the other models, which is like, okay, this model is identifying overdispersion, like models which does not account for the overdispersion and the models which account for the overdispersion. It's clearly distinguishing between that. Also, Poisson normal is actually coming very less. That means this model is clearly models for the random effects as well. It does not identify the parent model as such. And also the envelope width does not make much difference to it. So we say that, okay, this is working for higher sample sizes, and envelope width and G of B doesn't really matter much. And it can identify the overdispersion. So we see that with the negative binomial with the quadratic variance with higher one of the functions, we see the same results. For higher sample sizes, it actually identifies Poisson very well, and the Poisson normal is going very low. That means it really can identify overdispersion. So the key takeaways are the framework works better for the overdispersed data with higher sample sizes, and penalization with respect to the boundary distance has no effect, and penalization with respect to the envelope width also has no effect. So the next steps are we want to consider large sample sizes, misspecified models, and we think that why the function does not have an effect, like G of B does not have an effect, is because its baseline is pretty low. So all the functions are almost having the same value. So in effect, it's all behaving the same. So if we increase the baseline, maybe it has an effect on the distance, like the base distance. And we also want to penalize with the number of parameters, because the Poisson has a single parameter and all the other models we considered has like 2 parameters. So we want to penalize for that factor too. And these are the references, and thank you. That's all. And thanks everyone, and thank you for having me here.
Thank you so much, Darshana.